So welcome everybody to the, I guess, the first colloquium of the year. So with the permission of the speaker, I want to start by thanking the three organizers, Gabriel, Abelio, and Jaime, for sustaining this for a year now and keeping it going. I think it's a very nice thing for everybody, so thank you. And now I have been asked to present Jaime. So most of you know Jaime enough, but I'll say a couple of words about him. So he's a mathematical engineer from right here, from DIM, Universidad de Chile, and he's a PhD in statistics from Purdue University, and also a professor here at the faculty. He has made lots of contributions in different subjects in probability. I can mention stochastic analysis and SDEs, in particular backward SDEs, the theory of quasi-stationary distributions, and also potential theory and ultrametric matrices, which is what he's going to talk about today, I guess. Maybe some connections with a little bit of stochastic analysis. So Jaime, on top of this, has a long history doing many things for CMM and for the university. In particular, he was the director of CMM for 4 years, I guess. He funded the astroinformatics lab at CMM, and he's also the director, and he was like the main force behind starting the HPC lab, the Laboratorio Supercómputo, NLHPC at CMM, which gives service to all, to many institutions in Chile. So he has a long history of making lots of contributions to math in Chile. And he also has had lots of students, many of them here, one of them in front of you right now. So, and of course, he was very recently awarded the National Prize in Science, for which we're all very happy. So it's my pleasure to leave you with Jaime.
Okay. Los agradecimientos los voy a decir en español. Gracias a los organizadores, Gabriel, Abelio, Ana. Un placer estar acá. Hacía mucho tiempo que no daba una charla en el DIM-CMM. Está llena la sala, es genial. Venimos saliendo de una charla de Jean Dolbeau. Estoy absolutamente fatigado mentalmente. Jean nos dejó muertos. Así que 200 sí estoy un poco lento. Okay, the talk today is going to be about ultrametric matrices, and I start with a picture. My main collaborators are, of course, Silvet Martinez. I have been working with him 40 years now. Wow, 42 years, actually. Pablo Darnell was initially also a collaborator. We did the thesis together, so we were together in our engineering thesis or memoir. I don't know how to say that. And during the cocktail, I can say something about that thesis. Gerard Michon, the first part is going to be a. I don't know how Gerard Michon got to that result, and we prove it not like 40 years ago exactly. And then we collaborate a lot with Claude Delacherie and a Chinese guy that was visiting the CMM, Xiaodong Zhang. Okay, what is ultrametric distance? Okay, I have a, thank you. Well, an ultrametric distance is a distance that satisfies a very strong triangular inequality. Okay. That make it a little, that makes the geometry a little weird, okay? In particular, and that will explain that also. In particular, because if you have two balls of the same radius that intersects, then this distance is less than r, this is less than r, and so the distance between x and y is less than r as well, okay? So actually they are the same. So the picture is wrong. Two balls of the same size, if they intersect, they are equal. So this means that balls of radius r form a partition of the space, okay? And most of the talk, the space is going to be a finite set. So here, where these distances come from? Well, I think the first use of this distance is exactly to classification, because this allows you to classify objects in a finite set. But also there appear applications on physics, also in special spaces, so a special completion of R, of Q with that, with your non-Archimedean space and so on. But most of the talk is going to be about classification, okay? So just start with I will speak about the tree. So an ultrametric distance is equivalent to a tree. So you have 4 objects you would like to classify. So the distance between the maximum distance in the space is something of order 1 over this number. Okay. So at 1, they are all together. So it's the maximum distance, it's the diameter of the set. Then at distance 1/2, I will explain why I'm writing in increasing order, but not the distance. So 1 and 2 are together at that level of magnification. 3 and 4 are together. The next level, 1 and 2 are separated. 3 and 4 are still together at level 4. And then 3 and 4 are getting separated. And so I put that in a matrix, okay? So this indexes tells you how this thing will go. And you're interested on the leaves of the tree, but also you are interested in the intermediate states, okay? So in a way, I will tell you why we need the whole tree to explain what we need to explain, okay? So instead of having a distance, you have a matrix U, which is essentially U. Essentially, U is 1 over distance. Of course, in the diagonal, it's not infinite. It's a finite number, okay? So any questions about how you construct this matrix given these weights? Or vice versa? Given the matrix, how to construct the tree? Okay. So the diagonal, the other way around, I will try to construct the matrix given the tree. Okay, so you have the leaves for the moment, and so you go. What is the entry 1, 2? You go to the level where they got separated, and you see the height of that. Okay, and in the diagonal you fill in the same way. Okay, so it's okay. In the direction from the matrix to the tree and tree for the matrix, okay? But since I'm interested in the whole tree, not only on the leaves, then you can do the following. You can add these intermediate steps as a new nodes and do the same thing. Then you will have a matrix 8 by 8, and then the original matrix is a block of this matrix. Okay, so B got separated from C at level 1, so the entry should be 1. If everything is okay, B, A is 1. Okay? All right. So I can get ready of this now. Well, I will keep it for a moment. I will keep it for a moment because the people have to enter into that. Okay. You have a tree. Yes, in increasing order, and the distances are 1 over. Yeah, the weights have to be positive and increasing. So this means that the distance goes to 0. Huh? So in a way, 1 and 4 are very separated apart because the distance is like 1 over this number, 1. But 1 and 2 are close because the distance is 1 over 2, which is smaller. So u and the distance are related by that. Okay. So an ultrametric matrix is a non-negative matrix. I can define it without the use of a tree. U non-negative, most of the time is strictly positive for me, okay? It's symmetric and satisfy this inequality. Which is the reverse of the inequality provided by the ultrametric distance, okay? And so you have a tree of that type, and Gerard Michon was visiting us in 1994, and he announced a result about ultrametric matrices without any proof, and we don't know where he came from, where he got that result, okay? So he said, I think I can prove that a matrix like that is more or less always non-singular. Non-singular. The inverse has this shape. So positive numbers on the diagonal and negative numbers in the off-diagonal entries. And the sum of the rows are non-negative. He said that he came using electrical circuits, intuition. He was right, because after that we understood that this is related to the Kirchhoff law. But he has no proof. And so we Cerveta and Michon proved that result 40 years ago. And we sent that to a linear algebra journal, actually, a SciAm journal. And the editor was Richard Varga. I think Mike knows him or knew him. He died like 2 years ago. I never met him, unfortunately. And he said, your result is very interesting. I said, why? It's so interesting. He said, this is an old problem. We solved part of an old problem. And the old problem is not this one. It's related to something that is called M matrices. And M matrices are very important. I will show you why. They are matrices that has positive and negative numbers, positive in the diagonal, negative in off diagonal. So it's like a U minus 1 plus an extra property. And this is a book with, I don't know, 30 different extra properties that give you equivalence definitions. And one of them is that M minus 1, which is our U, is non-negative. Okay? These matrices appear in many places. Normally, when you discretize an elliptic operator like the Laplacian, you get something of that type. I will try to explain why. So other numerical analysis algorithms, the matrices that do the iterations have that shape. And why they are so important? Because they produce a stable algorithm, actually. So this characterization is well known. You have many other equivalent relations. For example, one very interesting, at least for probability, is that there exists, so you can add that or you can add the following, there exists a diagonal such that M times D is rho diagonally dominant, which in matrix means that the element in the diagonal dominates the sum of the other ones, the absolute value of this, the sum of the absolute values, okay? So it's like our property here. Yes? Every entry. Positive means here point-wise, okay? It's not, it's also positive definite, but it's more specific. Well, if M is symmetric, M is positive definite also. The problem, yeah. No, not in general. So this is, the ultrametric matrices are very small piece of the space of this type of inverse matrices. So the main problem they have is what are the U's that U inverse is M matrix? That's the main problem. If I give you a positive matrix, is that, of course, before you invert it, it is an M matrix. This is an M matrix, inverse M matrix problem, which is quite tough in linear algebra. And I will try to explain why it's tough. Okay. Now I will go to give you some ideas of how we prove that, and then a modern proof of that result of Michon, Servet, Martinez, and myself, using just block analysis for matrices. Can we take this up? So our proof was based on something that we developed in my thesis with Pablo Darner. And we understand a little bit operators of this type. Operators, lambda, that can be written as, I will try to be as simple as possible. So H of t, dAt. So for those that study a little bit of probability, A of t is a conditional expectation. They are particular cases of projections in L2. So if you look at this as from the analytic point of view, you have L2 of something. You have a projection. So you project so over a subspace of L2. And you demand that P squared is equal to P is self-adjoint. Okay. So this is a projection, but conditional expectation satisfies P of 1 is equal to 1, and P is non-negative, which means that P of F is non-negative if F is non-negative. So there are very particular cases of projections. And there is this is a nice background. And in function analysis, every self-adjoint operator has a decomposition like that. It's called the spectral decomposition, which is a generalization of the eigenvalues and eigenvector decomposition for a symmetric matrix, okay? So we were looking at what type of operator has a spectral decomposition where this is, those are given by conditional expectations, okay? So we did a little study of that. Well, that was exactly what we used to solve this problem. So we prove that if, first of all, there is a natural measure that satisfies that U of mu is constant. In the language of potential theory, mu is a measure, equilibrium measure. So we learn in physics that with the potential, electrical potential, if you have a conductor, there is a distribution of mass on the boundary that produce a constant potential. Okay? It's exactly that. So the first step is to prove that mu exists. And mu is a probability measure. Okay, the second step is to construct an operator. Okay, and the operator is quite simple. Lambda of x at I is equal to sum uij, xj, uj. Okay? So u is the kernel with respect to that measure. The fact that u is symmetric, lambda is self-adjoint. And the third step, which is a little more complicated, the combinatorics is there. You prove that lambda has a decomposition like that. Okay? That lambda is something like gamma p equal 1 to some number k. So those are the eigenvalues. E of gamma, E of p minus E of p minus 1. And so these are conditional expectations. So they are projections. And this is finer than this one. So this is the third step. Every matrix of that type has a decomposition of this type. But we need to pass through this measure that makes the things simpler, because then you have the whole theory of spectral decompositions. Let me show you examples of these matrices, because this is interesting. So I'm assuming the space has size 4. So the basic one is the mean value matrix. So it's constant 1, and then divided by 4 if you want to have a projection. So this is the basic project over the constants. Okay. If you want to project to other spaces, for example, you have this one. So this thing projects over the space where the first two coordinates are equal and the third and fourth are equal. Okay. And all of the conditional expectations are of this type. You have a sequence of atoms, and then you put uniform mass if the measure mu is the Lebesgue measure. That means equiprobability. Okay. But then, and this is the crucial step, we prove that gamma are positive and gamma are increased. So in the example, we have something of this type. The matrix U was 1 here, 1 here, I guess, was 2 here, 2 here, 4 and 4, 4, 4, 5, 5. So the gammas are related to this block structure. This should be row 1. This should be row 2, row 3, and row 4, I guess. Well, once you realize that the invariant spaces are like that, you just evaluate and you get the answer. So you define the eigenvector, and then you get the eigenvalue. This is the way we prove it. And so you now have a formula for the inverse. So you just invert the eigenvector, the eigenvalues. If you formally multiply, that gives you the identity. Or the thing you learn in the first course of linear algebra. If this is the composition, then 1 over lambda are the eigenvalues for the inverse. Okay. And then the monotone property of gamma, which means that this is decreasing, proves that lambda minus 1 ij is negative. So this finishes the proof because lambda and mu, u and lambda are related by lambda is equal to u times d. So the inverse of lambda is the inverse of u except for a diagonal. So the signs of diagonal elements are the same. Well, a long proof for something that now we can prove in 5 minutes, a full proof. Okay, I will do that because it's also important. So we didn't realize at that time something that Richard Varga did. By the way, Richard Varga and a collaborator proved the same result using linear algebra techniques. So they still rely on our proof of that is a little harder. And they noticed something that we do not notice at that time, that every ultrametric matrix can be decomposed like this. A and B. A and B are ultrametric again. Alpha is the minimum value. So it's the 1 in that example. And the two matrices also are ultrametric. Okay. And the values in A are bigger than alpha and B also bigger than alpha. And so the inverse, if you write it in terms of blocks, this is the transpose of that. Okay. So this is not it's a rectangle, it's not a square. Okay. Okay. E transpose E, whatever, doesn't matter. So if you multiply them, this is the sure complement. If you have never seen it, it's very important for numerical analysis. So if you multiply that by that, we'll give you the first equation, A times C plus alpha, 1I, 1J transpose E transpose equal identity. That's one equation. So there are two unknowns. And the second is you multiply that by that. So alpha 1 J 1 transpose E alpha times, let me see, C plus BA prime equals 0. You write down the equations using block analysis. You have two unknowns, C and this matrix. You obtain E from here, you plug in there, and then you get the famous sure complement, which I will write for you. So the sure complement is the following. You have A minus alpha square 1J, 1I transpose B minus 1. B minus 1 will be here, okay, when you get and the proof is finished. Why? The only thing to prove here is that, well, B is a block of an ultrametric matrix in an ultrametric matrix. So there exists a mu of that type, mu B. So this is, except for a constant mu B. So transpose mu B is the mass. Okay, so you have here the mass. So this is A minus alpha square mu bar B times 1 transpose. So you are having a ultrametric matrix and you subtract a constant. And the only thing you need to prove that this is less than alpha, the minimum possible value in A. So you have an ultrametric matrix. The inverse has this property that I mentioned, the theorem. So you do it by induction. So C is the inverse of an ultrametric matrix. C has plus, plus, minus, minus. You plug in this here, the sum of the rows of C or the columns of C are positive, so the matrix E prime is negative. And that's it. So the theorem is quite simple to prove once you have that. Why I did that? Because I would like to see what is the inverse of an ultrametric matrix. So when we saw that, we realized that our result was about probability, not about matrices. Because and you get the following. The inverse of an ultrametric matrix is positive on the diagonal, negative outside the diagonal, and the sum of the rows are positive. So you can factorize a constant, and then you get E minus P. So the constant is, I don't know, the maximum in the diagonal. You factorize that. The number in diagonal is less than 1. This is what it says here. The off-diagonal elements are negative. This means that P is positive. And the sum of the rows are positive means that the sum of P is less or equal to 1. So it's a probability kernel. So the inverse of an ultrametric matrix has an underlying Markov chain. And this is the moment the fun starts for us. What is U? And why is important U? And this is related to Jean Dolbeau's talk today. The inverse of U, the U is the inverse of I minus P. Forget about the constant. The constant has a meaning in probability, but forget about the constant. Let's assume it's equal to 1, okay? So the inverse of I minus P is the famous formula, the sum of the powers of P, okay? Since this is invertible and the matrix, the inverse is positive, then the spectral radius of P is less than 1. So the series of the powers of P converges, okay? If you have a doubt for that. But what is that? Okay, what is that? Is the potential. As much as the green function is the potential of the Newtonian kernel. So Uij is equal to, well, the first term is 1 or 0, but then it comes these terms. All right. What is Pij? I will give you an intuition. Pij is the probability of going from I to j in one step, okay? This is the meaning of Pij. What is P squared? P squared ij is the product of the matrix P times P. So it's the sum of Pik, Pkj over K. So it's the probability of going from I to j in 2 steps. All right, so this is the sum we're considering here. The probability is going in 0 steps, so you start I equal j, in 1 step, in 2 steps, in any steps. Well, actually, that is equal plus, I will change P by expectation, xn equal j, starting from I, and xn is the Markov chain associated to this kernel, okay? So associated to every kernel that is positive, substochastic, means the sum of the rows is less or equal to 1. You have an object that is called a Markov chain. It's a process that has takes values in this space of where I and j live, and gives you a realization of this simulation. You go from I to j with probability Pij, you go in 2 steps, etc. But here you can interchange sum and expectation because the function is positive, so it's Tonelli's theorem. What you get at the end is the sum, expectation, n bigger or equal to 0 to include the first term, indicator xn equal j. Starting from I. So here you count how many times you visit the node j in the whole history. All right? So this is the potential. This is the number of visits to j starting from I. And so at the end, it was correct, Gerard Michon. He thought that the matrix U is the potential of a certain electrical circuit. What is the circuit you construct? Well, you have to know the connections of this chain, what are the graph underlying this chain. I will try to explain a little bit how you get that. You have a graph, let's say there's a sort of tree, okay? It's more complicated than that. What is Pij? Pij is 1 over the resistance. So you put resistance here. The value of the resistance is 1 over Pij. I think that's called, I forget. One of the conductors. The conductors. Pij is the conductance of the and then U is the matrix that provides you the potential in every node. You fix a node, or you put the 0, and then you measure with a tester, and the thing you measure is U. And so it's a potential. And so the inverse has to be an M matrix. Where he come that for, I don't know. Maybe it's time that I connect to something that people in PDEs will love it. Because this is too discrete, probably for most of you. Not for Markov, but not for me either. So if you have R3, or a bounded domain in R2, or a Greenian domain in R2, and you run BT, a Brownian motion. Brownian motion. So it's a continuous time, continuous space process that the transitions are given by a Gaussian random variables, and the increments are independent, okay? That completely describe, and the variance is 1, okay? So you do the same. You count the number of times the process visits something, and you integrate, okay? So since the Brownian motion in 3 dimensions is transient, one thinks that this quantity is finite. At least the total time that visits a given point is finite. But that doesn't mean that the expectation is going to be finite, but it's finite. It goes fast enough to infinity. The Brownian motion starting at 0, goes around, and then lives fast enough to infinity to make this expectation finite. And what is that? Is the Green function. And this Green function is exactly 1 over the Euclidean distance. In our result, U is like 1 over another distance, which is an ultrametric distance. And these are the only 2 known cases where a potential is the inverse of a distance. Okay? In the discrete spaces, ultrametric distances. In continuous spaces, in R3, because in R4, it's no longer 1 here, it's 2. It's 1 over the distance, okay? So it's the same sort of result. And the inverse of that, in the functional analysis sense, is an M matrix. It's minus the Laplace. Okay. I will be back on this example a little more at the end. Okay. Questions? Pardon?
Do you know which piece gives you an N matrix? Or
Which?
which piece? Which
All of them. Transient, transient, recurrent, transient, no, irreducible, transient, irreducible is enough.
for them to be an ultrametric matrix?
And this is the thing I'm going to answer in 1 minute. So as Avelio said, if you take any P, irreducible, which means that the underlying Markov chain, you can go from one point to another with positive probability. Or the graph associated to that, e.g. belong to E, if and only if Pij is positive, is connected. Okay? Otherwise, you decompose in the connected components. You're assuming that the sum of Pij is less or equal to 1, but you need to be transient. At least one of the nodes is losing mass. Okay? So in your graph, at some point, you're losing mass. Otherwise, it's not transient. Then this thing, and I don't know, Perron-Frobenius theorem tells you that the principal eigenvector is less than 1 strictly, so the sum of the power of P exists, and this is the potential. It's equal to I minus P. So essentially, you have, for every matrix of this type, you have that this is a potential. How many degrees of freedom you have? Of order n squared. Well, if you put symmetric, it's n squared over 2, more or less, no? So potentials live in a space of n squared over 2 matrices, positive matrices. Ultrametric matrices have 2n minus 1 free quantities. Why is that? Because another way to construct ultrametric matrices, after a permutation, you have a freedom on the diagonal, and then you choose the upper diagonal. Okay? So there are some relations between them, okay? But from the point of view of degree of freedom, is no problem. And so you complete. How you complete that? The minimum of these two. So that's fixed. Continue in that way. The minimum of these two gives you that. And then the minimum of these two gives that. So you have n minus 1, 2n minus 1 degrees of freedom. So they are very small. Okay. How much time I have? 5:20. 4:30 partimos. Ya me comí 40 minutos. Okay. 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 I have to run. I have to run. Let me mention two operations that we probabilists like with Markov chains. One is the following. You have a Markov chain living in a space E, and you would like to induce it over a subset F. Okay? There are two ways of doing that. One is the following. You start from here. In the discrete time, it's easy to do it. In continuous time, it's a little bit tricky. But you start here. Let's assume that the chain in the bigger one is transient. Okay? So you start here, you jump, I don't know, you will jump outside. Oh, you go to the cemetery. Probabilities like cemeteries, okay? So this says that the Markov is transient. In a second run, you start here, you jump to the same, you were lucky, you jump another, and then you enter again to the set where you started. And so you say, I connect this with that. I forget about the intermediate steps. All right? So I jump from here to here, and that defines a new Markov chain. It's not that easy to see that defines a new Markov chain. So you forget about what happened in the complement. So the first entrance to the set F, you say, this is my new step. So this is x0 equal y0. This is x1, x2, and this is y1. Well, the others I forget. It's quite simple to understand that this new chain is also transient because there is chances of dying before ever entering to the set, okay? So it's more transient than the original, in a sense. But the number of visits from this point to that are the same in both chains. I don't care about this when counting how many times I visit that node. So this sort of thing is telling you that you have a potential at the level of E, and the inducer potential is simply a block. So the potential here, this is F, is just a block of B. So it's a nice thing. You induce a potential on a subset just by restriction. Okay? And the underlying Markov chain is exactly that. There's another way, which is a little more complicated. The same thing. You have E, you have F. I will make F a little bigger. And so you start from a point X. And as soon as I leave F, I kill the chain. Okay? So the chain can jump directly to the cemetery because the original one did that. Or, I don't know, it's balanced around here. And as soon as you get there, you kill it. So this is a whole killing state, an extra killing state. Okay? So they are quite different. This survives less than the original. So the potential here is less than U. Potential here is much larger. This will not count in that one. And what is this potential W? Is the chain that never leaves this set until you kill it. So this is the Green function for the subset. This is the Green function for F. In the Brownian context, you will cut this thing at the time you are out of a certain omega. You do the same. You count the number of the time that the Brownian motion before exiting the domain. This is a point y, and that gives you the Green function. So this is the standard Green function of a domain. And this is another thing. This is it's like saying I pick the Green function on RD, and I put an indicator function. Right? So both coming from different things in probability that are okay. What is the transition here? The transitions are not simple because what is the inverse of U is not the inverse of B block F. It's not. So this is a block of B. The inverse of that is not the inverse of B, but it's the sure complement. So here is the sure complement of the inverse. And here, what is W? Well, here is nicer because the transition probabilities is just you take the P for E, and you reduce it to F. So this is like restriction on the transitions, and then you get the green function induced. Here you have the induced potential, but the probabilities are difficult to get. Okay. Okay. The last piece of information I will give you is the following. We proved the following 2 or 3 results. If U is ultrametric, then there exists an extension B, ultrametric, which is of 3 type, like the 8x8 matrix I showed you at the beginning. Yeah? Can we show it again, maybe? Maybe I have share screen. Okay, there's a way of by enlarging the space, there's a way of embed this matrix U in a very special type of ultrametric matrices. Okay, that's the first one. The second one, this B, the inverse of B, has a graph exactly the same tree. So when you have this type of matrices given by labels, you're not looking only at the leaves, the whole thing, the underlying graph for the Markov chain is exactly the same tree, which is not. ¿No baja? Sí, sí, gracias. Which is not, I don't think it's necessary. That I don't think it's intuitive, but it has to be the same tree. I don't know. So this matrix U is ultrametric. You embed it in a larger one that has this form. This is very special. You have a tree, every node counts, and you have this hierarchy. The inverse of this 8x8 matrix is supported in the same tree. And the conclusion is 3. U is the restriction of B, and so we have this type of restrictions. So the transitions, remember, are given by this. You jump from one node to the other if there is a path in the larger space that connects that with that without visiting this small set. Okay? So the connections Pij for U is I is connected with J if and only if, or Pij is positive, if and only if the path Ej on the tree. The nice thing about a tree is that for every pair of nodes, there is a unique path connecting them called the geodesic, the minimal path. So you have to verify that for the geodesic. So the path connecting A and J do not enter to this small set. In our picture, you can do the inverse of U is supported in this graph. 1 is connected with 2 because there is a path, the geodesic, do not visit other nodes. So you have a one time transition from 1 to 2. You can go to 1 to 3 without visiting any other of the states 1, 2, 3, or 4. Okay. So what is the graph? Is the full graph. You can go from 1 to 2, from 1 to 3, from 1 to 4, 4 to 3. Okay. So the graph of U can be the full graph. In this example, is the full graph. Okay. But I give you a machinery to construct the graph of U. The second is, what type of graphs can we recover? This is a question about graph theory. I give you a graph, a connected graph, non-directed, and I ask you the following. You have a graph. This is your graph. you select a subset of nodes and you ask yourself, can I go from this node to this one in the larger graph without visiting no nodes of this small set? So let's call that the induced graph, okay? Which is not a subgraph, okay? Which graphs can I get from a tree? This is the question. Those are the only graphs that an ultrametric can have. And so we prove that a graph is a graph of an ultrametric, or what are the graphs obtained from a tree, if and only if you have a cycle, then you have the full graph on these nodes. Full graph. Those are the graphs that satisfy that property. If you have a cycle on this graph, then you have the full graph. Let me explain you what I'm saying. So the full graph in 4 nodes satisfy that property. Okay, I take a cycle, that, and then I have the full graph. I take this cycle, and then you have the full graph on 3 nodes. Okay? You have a cycle on peak nodes, then you have the full graph inside your graph. If the graph verifies that, then it's the graph of an ultrametric. For example, this one, how you embed it in a tree, is easy. You add a node. The embedded graph here is the full graph. So the typical graph associated with an ultrametric is a bunch of, how you call that, cliques? No. But also you can have loops, okay? For us, it's important because then you connect to another full graph. This is the graph of an ultrametric matrix. Falta uno. Thank you. So this is our last theorem. We haven't not published yet this paper, but this is a thing about graphs also. And but the structure of the metric doesn't change. No. So the index will have different numbers, but it's supported over the same graph. This proof I can share with you the proof. Only with you. Now the proof in one direction is obvious. If you have a graph, embedded from a tree, then if you have a cycle, you can connect anyone to anyone. Because going from 1 to 3, there is a path in your bigger graph that connect both. Okay? And then you have a path here. And so since it's a tree, these 2 paths has to intersect. And so you have a path from here, pardon. You have a path there, you have a path here. So then this thing will be a path on your tree, and so it's a geodesic, and then this has to be connected before entering to E2, and so this is more or less the proof. The harder part is to prove that if you have a graph of this type, then there's an ultrametric matrix. The last thing for the people in PDs is the following. Maybe you will be interested by that. And I'm lucky because Abelio is in the audience and he knows how to prove the following thing. So we proved like 10 years ago that if you have a potential, so This is not necessarily ultrametric, it's general. The inverse of a matrix of the inverse of an M matrix. So you have a potential. Then you can compute the n power of that, the n power in the sense of Hadamard, which means that is the is related to the product every first year student would like, that we use in the linear algebra, which is to compute the n power of the entries. Okay. This is very simple to see if it's invertible. There's no problem with inverting matrices in that way. So then we prove theorem. U to the power alpha is a potential for every alpha bigger or equal to 1. So for every alpha, if U comes from a Markov chain, U to the alpha, according to that rule, is also potential. Means there's a Markov chain underlined. So if you take the green function, which is proportional to 1 over the norm of x minus y, and you raise to the power alpha, is again a green function. Here there is a problem of integrability, which you don't have at the level of matrices, and alpha has to be bigger or equal to 1, unless that this is 3 over 1, 3. So the general formula, if you have n and alpha, n minus 2 alpha, in dimension n, alpha has to be, I think it's n over n minus 2. What is the process associated to that? So the green function in dimension 4, look at the dimension 3, the green function 2 in R3, a constant divided by 2 is a green function. There is a process. I can show you the simulations of that process while you do some questions. So I finish, and I will leave here the simulations. So in this case, alpha equal 2 is well known. It's called subordinated Brownian motion. Let me run it again. There is a blue simulation here that goes fast, and a red simulation there that goes normal. So time is, 1 unit of time is, some simulations stop immediately. So I'm a lousy simulator. Okay, so you see the red and the blue, no? You're not daltonic. Some of the, well, no? I have many friends that are daltonic, so. So the blue one is the Brownian motion, the one associated to the green function, the normal green function in R3, one of the norm. The red one is a time change of that. So you have a process that is running at time normal, and then you compose with a time that has this shape. So it jumps. The time change jumps according to an extra Brownian motion. If you are like to see why is that, I can explain you. But you have a time change that is almost flat and then jumps from 0 to 5. So you are following a curve that is continuous, but you jump from 0 to 5. The resulting curve, the red one, is not continuous anymore. Okay? So we know that the process associated to that, we know exactly which one is. It's a Brownian subordinated with a Leavitt process. And the green function is the square of the normal green function. And the fact that this process is discontinuous has impact, as my friend Abelio said, on Gaussian free field. So you should give a talk on that.
Okay, let's
Oof.
thank Jaime.
Sorry.
Okay, so if there are any questions, maybe let's take one or two from the audience on top of the ones we already had. Avelio?
Mostraron buena paciencia.
I had one. So can you get an ultrametric potential in the continuum? Do you know something
Yes,
about?
yes. There is only one example because essentially one example in the continuous because underlying graph has to be a tree. So it's the one-dimensional Brownian motion on the interval reflected on 0 and killed at 1, for example. So the underlying graph has to be a tree, and there are not too many in continuous. You can imagine a tree where the connections are pieces of intervals. I don't know, maybe. But this is an infinite tree. Yeah, we have a paper on that, and not always it's ultrametric. There's something about the boundary. If the tree is absorbed at the boundary, let me see. If it goes fast to the boundary, yes, it's ultrametric. But if not, no. There's an harmonic difference between the potential and the ultrametric.
Change that. You see it, you don't see it in the tree, just like in the.
Yeah, but you need a tree structure, not 3, not D.
Okay, any other questions? I had a very quick one. The C of 3 that you got from the, not there in.
Here?
C that you get there, but even in the simple case. Of
Well,
Brownian motion.
here you have
Yes.
a constant, no?
Right, so that
Cn. And here, formally, you would get Cn square, no? C3 square.
yeah, but even.
But the constant you get on the subordinated is a different constant.
It was
That you remove with a time change, linear time change.
even simpler. The C, of course, is the same C as in the ultrametric case, where you get the C in front of I minus P.
Has the same interpretation because it's a time change. So you can change the C as you want. If you run the Brownian motion at different speed, you just multiply by 2t, then you will get a half, maybe a half term. Yes.
Okay.
So t, yes, a half term.
If there's nothing else, then let's thank Jaime again. Yeah.
So it is in the fifth floor, we have the cocktail classical.
¿Hay hielo? ¿Hay hielo?
Sirve para resolver métodos numéricos, ¿no?